All right. Good morning again, colleagues. So let's
Morning.
start. Let's start with, I guess, the previous class that we had. We were talking about the Hamilton-Calais theorems. So now let's carry on with the definition of eigenvalue and eigenvectors. Then eigenvalue and eigenvectors. I guess you see my screen, right? Hello?
Yes, we can see.
My screen?
Yes, sir.
Yes, sir, you can see your screen.
All right. So now, let me start by doing like this. We start the definition. Let's start with the definition. Our definition for eigenvalue and eigenvectors are as follows, colleagues. Then, let's say you have a non-zero. You have a non-zero. You have a non-zero. Let me use this definition, this non-zero vector. Non-zero vector. Let me come up with this. It's called an eigen. Is called an eigenvector. That sign is called an eigenvector of, okay, fine. Before we come here, before we have this, let me define something, because you are going to say, where does this one come from? Before we have this, let's start here. Remember this thing, we have done the eigen, okay, the eigenvalue problem. On the eigenvalue problem, you wrote test number 2 about a linear transformation. For a linear transformation, remember we're dealing with maps there. So let's say our map is this sigma that takes vector v to this vector v. And then find all those scalars. And then let's say our scalars is this lambda and associated vector. Let's come up with this sign here, for which our sigma of this is equals to lambda of this. Is it fine, colleagues? And again, this is box number 1. Then number 2, let's check this one, where you say, remember on the Hamilton-Calais theorem, we were dealing with a square matrix, because we are going to calculate the determinant of that to get the characteristic, polynomial and characteristic, and then polynomial and that one of matrix. Then for an n by n matrix, if we have this n by n matrix, which is A, and we find all the scalars, in our case, this is our lambda scalars, such that the equation which is this A, matrix A, multiplied by some other books. I'm not going to bold this, but let me use this x bar. We agreed about this. It's equals to this lambda together with this x bar. Do you still remember that? Has a non-zero. As a non-zero. Remember, in your case, if you have n by 1, you know that the number of rows are n, and you are dealing with one column for that x for solution of this x, vector x. Let me put this. So after this, are you done copying, colleagues? For those who are copying?
Yes.
So we must agree, show respects. Then we must check the following. If we have this x be an eigen, that x be an eigenvector of the n by n matrix A, corresponding to an eigenvalue, where our eigenvalue is this lambda there. Then the vector which is A multiplied by this x bar is a scalar multiplication. It's a scalar multiple of this x. It's a scalar multiple of this variable x there. And then represented, let's say we have represented as geometric, say geometric vectors, which is this x vector and also A multiplied by this x vector, have the same direction. If this lambda is positive. And the opposite direction if lambda is negative. Are you still there, colleagues?
Yes.
Yes, sir.
Yes.
So now
Yes.
we are saying this variable, this vector x together with that ax are parallel vectors. So now let's take the definition of eigenvalue and eigenvectors. Let me take the one, okay, fine. Let me take this one, it's a little bit clear. So let me take this one. The definition. Let a matrix A be an n by n matrix. N by n matrix. Then we have already talked about the scalar here. The scalar, we have already identified that the scalar that is called eigenvalue. That lambda is called eigenvalue. The lambda is called eigenvalue. The eigenvalue of matrix A when there is a non-zero, vector, such that we have already talked about the parallel part of that, such that your A multiplied by this vector x will be equals to lambda multiplied by this vector x. And then vector x is called, we have already talked about this on the previous paragraph, is called the eigenvector. Can I get yes from you, colleagues?
Yes.
Yes.
All right. So let me see if there's something that I want here. Okay. Right. Okay. So I want to come up with something here. So from on our side, on today's Friday, on Wednesday, there is somewhere where we talked about the characteristic equation, if you still remember.
Say,
We talked about, yes, sir?
can you please go up a bit?
Okay. On Wednesday, we talked about the characteristic polynomial together with characteristic of polynomial and matrix. Are you done copying, sir?
I'm finishing.
So this definition, I defined this definition. I was not using the map. I supposed to use the one that has been defined by this map here. So I decided to take this one, the one that is there. It's fine if you want me to use this map to define the eigenvalue, the eigenvector, I can still do so. So now let's agree. On Wednesday, we know, okay, from that definition where you said ax equals to lambda x are parallel or are equal, from the definition you have the following, colleagues. From the definition, when you say those two things are parallel, you are saying two vectors are parallel if what? There is two conditions. Check the definition of when you say two vectors are parallel, what do you mean by that statement? You have ax will be equals to this lambda x. And from here, you can come up with what? You can come up with your ax minus this lambda x will be equals to this zero vector. Then from this zero vector, You and me on Wednesday, we came, if we take out that x as a common factor, then you'll have a minus. Instead of having this, here you are going to have this I. Then outside you'll have this x bar. Do you agree? Then the whole of this will be equal to this is 0 vector. I'm waiting. On Wednesday, you were using this when you deal with the characteristic equation and polynomial. Do you still remember that?
Yes.
Yes.
So from this, do you still remember from Smta022 that if I have A multiplied by this I, the answer will be equal to A. The identity multiplied by that matrix A, the answer will be A. Do you agree?
Yes.
All right. Thank you very much.
Yes.
Yes, sir.
So now, this is just a repetition, but it's fine. Let me take you through. Let's say you have this one as equation number 1, right? So now, it's a repetition of what we've done on Wednesday, but it's fine. Let's check this corollary. On the corollary, we have a matrix A, and that matrix is a square matrix. It's a square matrix. And then on this square matrix, you and me, we know about the homogeneous. The homogeneous system will be A multiplied by this vector V will be equals to this 0. Is it 0 or 0? Yes, it's 0. Has non-trivial solution. We did talk about this non-trivial solution if and only if and only if the determinant of that matrix A is equals to 0. If you still remember that, colleagues, can I get yes?
Yes.
Are you still there?
Yes.
Then
Yes,
now,
sir.
Yes.
again, so using what? Using this corollary, and equation 1. Remember what is equation 1 there? Equation 1 above. We can conclude even this one is just a repetition. We have already know what is a characteristic equation and polynomial, colleagues. Conclude that if lambda is an eigenvalue, with corresponding corresponding eigenvector. Remember, according to that corollary, we have this x bar there. So now, you and me, we agreed on Wednesday that you can come up with the characteristic equation, or you can call it the characteristic polynomial. It's where you said we find the determinant of that cx, if you still remember. On Wednesday, you and me, we did something like this. I'm going to delete. You said f of x will be equals to the determinant of this cx, if you still remember, cx. And then what is cx? Cx is equals to what? Is equals to a minus lambda I, if you still remember that, colleagues. And the whole of thing we agreed, we have even proved, there is an example that we did on Wednesday. We got what here? We got 0. Do you still remember that? The previous example where we come up with the polynomial,
Yes, sir.
characteristics polynomial, then you are going to substitute where there is lambda, or where is that lambda by that A matrix. Then we try to square, then later on we got that 0. Do you still remember that?
Yes.
Yes.
Sure. Then now, before I go to these examples, let me have this. Let me have this. This theorem. Let's check this theorem. Hello. Colleagues, then here you are. Then there is this theorem that comes here. So somewhere, somehow you may find that, do you hear me? Somewhere, somehow you may find that they call this one, I guess on Wednesday we're calling this theorem of f of x determinant where you got 0. You were calling it the characteristics polynomial, right? Or characteristics, is it characteristics polynomial or characteristics equation? We were calling it what? That equation where we get 0, colleagues?
Character equation of A.
You were calling it?
Characteristic equation.
Good. We're calling it characteristic equation. So if you call it characteristics equation, then we are sorted. Then now the theorem comes for that one. You already have something like this on Wednesday. If we have a matrix A, and that matrix A is n by n matrix, n by n matrix, then lambda, we agreed on this, lambda is an eigenvalue. The lambda is an eigenvalue of this matrix A if and only if and only if it satisfies, if it only if satisfies what? The characteristic equation. That characteristic equation. Characteristic equation of A. And you and me, we agreed on Wednesday that we are saying this thing is the same as the determinant. I'm going to take it from the determinant side, colleagues. The determinant of a matrix A minus. Remember, I said some other books, instead of saying lambda is an eigenvalue, they can use any scalar that they want. But here we are using this lambda as a scalar there of this will be equals to this 0. Can I get yes from you, colleagues?
Yes.
Everything is fine?
Yes.
So before I go further, let me come up with something. Let me see. We're supposed to talk about the definition on the subspace of eigenvalue 1, 2, 3. We'll see that one next year. But now, here is the most important part that you must know. The procedure for finding, the procedure that you are going to use to find eigenvalue and eigenvectors. The procedure to find eigenvalue, eigenvalues, and eigenvectors. Eigenvalues and eigenvectors. Number one, remember you are dealing with a matrix, a square matrix. Let A be the square matrix, or it's a matrix representing. Now I'm going to use the sigma map that we defined there when we defined that linear transformation, representing a sigma with respect to the basis, to some basis, to some basis. And in our case, to find number one, we agreed that you are going to get your characteristic of this, where you said it's A minus lambda I. Do you still remember this? We did that on Wednesday. Characteristic matrix. Then number two, you must find the characteristic polynomial. The characteristic polynomial. You and me on Wednesday, we agreed that now you are talking about your f of x, which is equals to the determinant of this, the determinant of c lambda. Sorry, where is that boy? Where is that guy? Cx, and you know that this one will be the same as the determinant of what, colleagues? Is the determinant of A minus lambda I. Do you still remember that, colleagues? We have done that on Wednesday. Are you still there?
Yes.
Yes.
Yes, sir.
Then,
Yes, sir.
Koza, where are you? You are not responding. You are the one who rectified me on Wednesday when I was saying f of x there instead of f lambda. Then number three, the procedure. You are going to solve the equation. You are going to solve the equation where you will say f of this lambda is equals to 0. You are going to factorize that polynomial of order whatever. If a solution exists, if the solution exists, the results are, remember the eigenvalue and the eigenvectors, we agreed that lambda is what? The result are eigenvalues. Remember the eigenvalues, that's where you are going to get the lambda is equals to 7, the lambda is equals to A, something like that. Then that's where you are going to have these eigenvalues. And then we say if there are many, they will depend. Remember here you are dealing with a polynomial of order n. We are generalizing, meaning when you factorize that f of lambda, you are going to get your lambda 1 maybe, or lambda 2, up until, colleagues, it will depend on the polynomial that you have, and etc. there. Then when you are done with this condition number 3, you are going to do what? Now you are going to check number 4. On number 4, for each For each lambda that you got, for each such lambda, let's say lambda 1, you are going to solve the equation. You are going to solve the equation where you'll say your characteristic matrix, which is C lambda. For now, I don't know what is that. Okay, fine. Instead of writing 1 here, let me put I. I will start from 1, 2, 3. It will depend on the lambdas, on the eigenvalues that you got. Then here, let me say the C of lambda I will be equals to, for the first one, you are going to have C lambda I, then multiply by this one, you dot it with this variable vector X. Your answer will be equals to this 0 matrix. Then now, solution to this equation. Solution to this equation are eigenvectors corresponding to lambda. Let me scroll a little bit, colleagues. The solution to this equation are eigenvectors corresponding to lambda I. Let me know if you are done so that you can take one example. We are going to follow those procedures there. Are you done, colleagues? Class rep, this class is going to end at what time? Exactly at 1 or what?
12.
Okay, sharp. Are you done copying, colleagues?
Yes.
Yes.
All right.
Yes.
So if
Yes, sir.
you are done, let's take this one. Example. Find the eigenvectors and eigenvalues of, you are lucky you are dealing with this nice one, 2 by 2, 3, 2 minus 1, and then 0. Then we close there. Are you still there, colleagues?
Yes, we're still here.
Yes.
Procedure number 1. We must come up with what? You must come up with C lambda, which will be equals to A minus lambda I. We agreed on this on Wednesday. Can I get a yes, colleagues? Procedure
Yes.
number 1.
Yes.
Then after getting this, what I'm going to have is the same as C lambda will be equals to, what is A? The original A is what, colleagues? Is 3, 2 minus 1, and then 0. I know you are very clever. You have already seen that here you are going to have 1, 0, 0, 0, 1. Then now, let's have this characteristic matrix. What is the answer? The final answer for this will be what? What is going to be the answer? Remember, the lambda will multiply that identity there. The first one, you'll have 3 minus this lambda.
3
You'll have
minus
this
lambda
minus 1. And then what?
minus,
Is it
yeah,
0
and then
minus lambda? It's the same as
yes,
minus lambda here, right?
yes,
So after this, procedure number 2, they said you must do what? You must find the determinant of this You must find the determinant of this C lambda. That's where you are going to get the determinant of this C lambda, colleagues, will be what? The determinant of this is 2 by 2, colleagues. You are not going to struggle. You have done this in SMTH012. What is the determinant of that C lambda there? Hey, to find determinant of 2 by 2 is a problem. Hey?
No. No, sir.
Uh-huh.
We're going to have 3 minus
3
lambda
minus lambda multiplied by negative
multiplied.
lambda minus into 2 multiplied by negative 1. And this f of lambda, f of this lambda will be equals to what? Is the same as lambda squared minus 3 lambda plus 2. Can I check with you if you agree with this?
It's correct.
Yes, it's correct.
Then let's agree. Let's check procedure number. We are on number what now? We are going for number 3 now. On number 3, they said you solve the equation of f lambda, you equate it to 0. So now you are going to equate this f lambda to 0. When you equate f lambda to 0, what is going to happen? You are going to have lambda squared minus 3 lambda plus 2 will be equals to 0. Then you find the factors of this if it's possible. Is it possible to factorize that quadratic equation?
Yes. Yeah.
You get what and what?
Negative 2
Lambda.
minus 2.
Very good, class rep. Lambda minus 2 and then lambda minus what? Minus 1.
1.
Can I get yes from you that these lambdas are what? Are the eigen what? These lambdas are eigen what?
Eigenvalues.
From this, you are going to get, maybe we can say lambda is equals to, we solve for lambda, do you say lambda is equals to 2 or lambda is equals to what? Equals to 1, isn't it? So
Yes.
now these lambdas, according to the definition, we call them what? Hence the eigenvalues. These lambdas are your eigenvalues. Our eigenvalues are, that's why we said lambda I will represent y equals to lambda equals to 2 and lambda is equals to that. So you can start by saying the first one, maybe if I say 1, colleagues, do you understand that I'm trying to differentiate these two lambdas? Can I say maybe lambda 1 will be equals to 1 and then number 2 you say lambda 2 will be equals to 2? I don't know
Yes.
if maybe you understand, or maybe can I put a here, maybe lambda a, for instance, lambda a and lambda b, in order to differentiate those two lambdas that you have. Is it fine? Can I put lambda a, lambda b, or can I put lambda 1, lambda 2?
Lambda 1, lambda 2.
So if you put lambda 1 and lambda 2, are you not going to get confused by this?
No, sir.
No,
Are you serious? So if you say you are not going to get confused, I can have lambda 1 and lambda 2 here. It's not a problem. Or if you want, you can switch them. If I want, I can still switch these two and say this one is going to be lambda 2, this one is going to be lambda 1. There's nothing wrong with that. All is well.
Yes.
So since you are saying you don't have any problem with this numbering lambda 1 and lambda 2, it's not a problem to you. Then now let's check according to the procedure. You are now on number 4. On number 4, we must solve. You must solve. Let's say for the first one, we must solve for C lambda. For lambda, solve for C lambda equals to what? C lambda is equals to 1. So in this case, our original equation is C of lambda 1 will be equals to C of lambda 1 multiplied by this variable x. Are we still together, colleagues? Then this one, what you are going to do, you go back to the C of x, this one. you are going to substitute where there is lambda on this equation. Where there is lambda, you put 1. So you are going to do that on this statement here. You are going to have your C lambda 1 is equals to 1, meaning you are going to have equal sign. Instead of having, okay, C of that multiplied by C of 1 multiplied by this X. That's when now you are going to come back here. You go to the previous one, you substitute where there's lambda by 1. What is going to be the row number 1? The answer will be what, colleagues?
2.
2.
Very good, 2. Then the second entry on row number 1, the answer is?
2.
Very good. Go to row 2. Element entry number 1 on row 2, the answer is?
Negative
Minus
1.
1.
Minus 1. Then the next one is?
Minus 1.
Very good. That vector, the vector 1, the vector of x, is up to you if you can come up with what, colleagues? Can you come up with what? Can I come up with x maybe if you want, or can I come up with maybe lambda 1, lambda 2? It's not a problem. I can come up here with lambda 1 and then, is it correct? Or can I use the variable x? Which one can I use, colleagues?
Use X.
It's not a problem. I can use lambda 1 and then lambda 2. If I use lambda 1 and lambda 2, is it going to give you a problem? Yes. Let me use x1 and x2. It's not a problem. You can come up with 2 variables there. Is it fine? So according to that procedure number 4, the whole of this must be equals to what? Must be equals to this 0 vector. So meaning here, you are going to have what? You are going to have 0 and then 0. Can I get yes, colleagues? Even here, if I want, I can still put this 0 vector there. I'm waiting. Can I get yes?
Yes.
Yes.
So for the first one, you multiply row by column. If you multiply row by column, do you see that the first row on row 1, you are going to get 2x1 plus 2x2 will be equated to 0. Do you see it?
Yes.
And then I guess you'll agree that x1 will be equals to negative x2. Do you agree?
Say. Wait.
Yeah.
Oh yeah. Yeah. It's correct.
Then from this, can I get yes from you that if now we say x1 and then x2, we want to write everything in terms of x2. What is x1? Okay, fine. Someone will say that. What about on row 2? Even on row 2, you can still check. On row 2, you are still going to get x1 is equals to x minus x2. Do you see it, colleagues? If you go to x2, you're still going to get the same story. You'll have minus x1 and then minus x2 is equals to 0. But when you solve for x1, you'll get x1 is equals to negative x2. Do you see that? Do you see that, colleagues?
Yes.
Yes, sir.
Then even if you use only row 1 is still fine. We know that x1 is equals to negative x2. Let me check. Can I check with you? What is x1? x1 is equals to what? x1 is equals to negative x2. Do you see it? What is x2? Your x2 is equals to x2. Is there anyone who have a problem to get that minus x2 and x2 there? All of you know how to get minus x2 and x2? Then from this, you take out your common factor of x2, you are going to have -1 and then 1. So now your what? I can say your eigenvalue 1 is equals to -1 and then 1, and then corresponding, this one is the one that corresponds to what? This one is corresponding to the eigenvalue, corresponding to the eigenvalue of lambda 1, which is equals to 1. Are you still there, colleagues? Do you understand? Is there any other question? All is well.
Yes.
Yes, sir.
All right. So you did not finish. Then now, for the second one, remember, you are now going for lambda, which is equals to 2. We are going for lambda 2, which is equals to 2. Are you ready? And that's where you are going to get your C of lambda 2 will be equals to C of lambda 2 multiplied by this variable x. The answer will be equals to this 0. You go back again. You are going to have your C of 2 will be equals to this one. You will have the C of 2, meaning where there's lambda 2, you put that 2 multiplied by this variable x. Your answer is going to be this 0 vector. Not 0 vector, you can say the 0 vector or 0 matrix. Then now you go back again to this original, the characteristic matrices. You replace where there's lambda by 2. You replace where there's lambda by 2 here. I'm going up, colleagues, on this star. On this star, replace where there's lambda by 2, positive 2. Are you there? Colleagues, where are you? I
Yes,
see
yes.
here you are
Yes.
going to, your answer will be what? Will be 1, 2, -1, and -2. Your variable, you said you are comfortable with x1 and x2. Then don't forget you have this 0 and then this 0. Again, from this is either you use row 1 or row 2. If I use row 1, can I get yes from you that you are going to get x1? You are going to get what? You are going to get x1 plus 2x2 will be equals to 0. Or this statement, if I want, I can write it as x1 is equals to -2x2. Are you there, colleagues?
Yes.
Yes.
Yes,
So
sir.
from this, you are going to have this. You are going to have the x1 and x2. You are now solving for x1 and x2. You write everything in terms of x2 if you want, or maybe you can write everything in terms of x1. It's up to you. Then here you are going to have the value of x1 is minus x2. And what is x2? Your x2 will remain x2 here. Then now you take out x2 as a common factor. Then you are going to have -2 and then 1. So now you got what? You got the eigenvalue for number 2. The eigenvector number 2 will be equals to -2 and then 1. Then is the eigenvector corresponding to, the eigenvector corresponding, it's an eigenvector corresponding to the eigenvalue, remember the eigenvalue is that one of lambda 2 is equals to 2. Or maybe even if I can simply just write responding to the eigenvalue lambda 2. Are you still there, colleagues?
Yes.
Yes.
All right.
Sir,
Oh, yes, ma'am.
are you not supposed to write -2x2
Oh, yes, you are right. Negative x2 here. You are right, ma'am.
Sir,
Yes, sir.
am I allowed to use one variable from the previous eigenvalue in the second value?
You mean, remember when you come up with the augmented matrix? When you come up with the augmented matrix, is it augmented matrix? If you have a system of linear equation, remember you are going to have a matrix X. After matrix X, you are going to have the variable capital letter X, or maybe as a vector X equals to the boom shack. Do you think that vector X is going to change those variables? Sure.
I'm clarified.
So let's check something here. So the examples that we are going to do now are common examples. Check this one. Example. Let me just write examples. On top you have determine if the given vectors x bar are eigen eigenvector of given matrix. And I saw something. Some of you, when you were writing test number 2, question number 4, where you were checking those two maps, you were simply just saying T and S exist. Then you say T and S exist. You don't carry on. After you say TS and R exist, you must prove, you must show us. You only tell us that TS exists, then ST does not exist. You were losing marks for that. So, like here, they are saying determine if the given vectors X are eigenvectors of given matrix. If so, determine. If so, you must determine the corresponding. You must determine the corresponding eigenvalue. Eigenvalue. Then number one, if we have this x bar which is equals to -2, 1, and then 1, where your matrix A is equals to 0, 0, -2, and then 1, 2, and then 1, 1, 0, and then 3. Are you still there, colleagues?
Yes.
Yes.
Are you done? Can we solve this one?
Yes.
Yes.
So here we are going to check. If you want to check for this one, your answer is going to be very simple. You simply go straight to the definition of eigenvalue. And we say that to see if this variable vector x is an already, remember those one of minus x1, is it -2 and then 1, they give, you have them, is an eigenvector. We must check if your ax is equals to your lambda x, vector x. Are we all together there, colleagues? For some,
Sir,
yes, for some,
can you please scroll
scalar
back?
lambda.
Can you please scroll back?
Everything is fine?
Thank you, sir.
Okay. So we have you know how to multiply. On your left, okay, we are going to replace whatever we have there, colleagues. Né? Can I get yes from you, colleagues?
Yes.
Yes, sir.
Or can I have, okay, on your left hand side, you have this ax like this. What is a, colleagues? A is 0, 0, minus 2, 1, 2, and then 1, and then what? 1, 0, and then 3. Multiply by the vector x. And our vector x, they give us that vector x is what?
Minus 2,
Minus 2, 1, 1.
1.
Wait, there's something that I don't understand here. Wait, I want to see something. Is minus 2 what and what?
1, 1.
So please put that minus 2, 1, and 1. After you do that, let's multiply and see what we are going to get. Are you still there, colleagues?
Yes.
Yes, sir.
Okay. We have, is it minus 2 here or 1? It's fine. Let's put minus 2 and then what? 1 and then 1.
Yes.
Is it fine?
Yes.
Yes.
So when you multiply this, what is your AX, colleagues?
Minus 4, 1, and 1.
You'll have what?
Negative 2,
Negative.
negative 2,
Are you not lying? Row number 1 multiplied by the column number 1, the red part, I see 0 plus 0 and then 0 plus 0 and minus 2.
Yes, sir.
Is it correct?
Yes, it's
Yes,
minus 2.
it's minus 2.
Row number 2 multiplied by that column, what's the answer?
Minus 2
Minus 5.
It's
plus.
minus 5.
Hmm?
Please check. It's minus 2
1.
multiplied by that minus 2.
Plus 2
I see minus 2 plus 2.
plus 1.
I see
Plus
1 here.
1. Yes, it's 1.
It's 1. Sir. It's
Then the row number 3, what is going to happen?
1.
1.
It's also equals to 1.
Yes.
Yes.
Then this one. Then on the right hand side, what do you have on the right hand side? On the right hand side, you must have what, colleagues? Remember, you must have lambda x. I'm right?
Yes.
Where you have lambda into, you are going to have lambda into what?
-2.
Lambda into -2, and then what?
1, 1.
1 and then 1. Is it fine?
Yes.
So what can you say about this? It's not, ne? These two
Yes.
things are not equal. Do you see that they're not equal? Are they equal?
No.
Why are you saying no, ma'am? I guess there is something wrong with this. That's why I was so stuck. Let me change and put number 1 as your x bar will be equals to, your x bar will be equals to -1, 0, and then 1. And then your a, we remain with our a as what? As 0, 0, -2, 1, 2, and then 1, 1, 0, and then 3. Is it fine? So in order to check if this one, same question, you are going to have your ax bar will be equals to this lambda this, vector this. I'm right? So for your left hand side, you are going to check ax vector x, and then that's where you are going to have your a is what? Your a is 0, 0, -2, and then 1, 2, and then 1, and then 1, 0, and then 3, multiplied by that vector there, which is -1, 0, and then 1. When you multiply these, colleagues, you are going to get your, you'll get your ax will be equals to into, when you multiply, colleagues, tell me row number 1, I see 0, 0. I see what? Please check it. I see 0 plus 0 and then -2. Row 2, please confirm if it's correct. Row 2 is going to be -1 plus 0 plus 1. And then row 3 is going to be what? Row 3 is going to be -1 and then plus 0 and then plus 3. Do you agree?
Yes.
And
Correct.
that's when you get this x bar will be equals to. When you add those things, you are going to get -2 and then 0 and then what? And then 2. Are you still there?
Yes, sir.
Yes.
Then if you want to see this, we started with the left hand side. Now I see that your ax bar will be equals to, you can take out 2 as a common factor there. When you are going to remain with -1, 0, and then 1. Can I get yes from you that now you are going to say your lambda is equals to 2, then your x bar will remain with what? -1, 0, and then 1. Can I get confirmation from you that now you have lambda multiplied by this x bar?
Yes.
Is it correct, colleagues?
Yes, sir.
Yes.
All
Yes.
right. So you are going to do the very same thing for this one. You are going to express number 2 as you have this x vector, vector x is equals to 1 and -2. And then again, they gave you a matrix of A where A is equals to 3 and then 0, 8, and -1. You are going to do the very same thing. You have a x vector x equals to lambda of this vector x. You must check if these two things are equal. You know how to multiply, colleagues. Can I get yes from you, colleagues? All is well.
Yes, sir.
So before we go there, maybe you can conclude here on the previous example and say what? indeed, your X bar is n eigenvectors. And lambda indeed is equals to 2 is the corresponding eigenvalue. I want to try something. Can I get permission from you colleagues? I want to try something.
Yes.
Yes.
Yes, sir.
So what I want to try, I want to ask to take it from the scratch when we have remember the previous example. The previous example we said to find the eigenvalue and the eigenvectors of, right? I don't know how can I, let me name this. Find the eigen. Let's see if we win. Find the eigenvector and the eigenvalue. The eigenvalue and the eigenvector. The eigenvalue and the eigenvector. I'm taking the very same matrix of that A. The first one, matrix of A, which is equals to the first one, colleagues, where you have 0, 0, and minus 2, 1, 2, and then 1, and then 1, 0, and then 3. Are you still there?
Yes.
So
Mm.
according to the procedure, they said you must come up with your Cx, right? Meaning your C lambda will be equals to, is it A minus lambda I? Is it, can I get yes from you?
Yes, sir.
Yes.
So from here, you are going to have what? You are going to have your C lambda will be equals to, make sure that the matrix, everything is fine, 0, 0, minus 2, 1, 2, and then 1, and then 1, 0, and then 3, then minus, here if I want, I can put lambda, 0, 0, 0, lambda, and then 0, 0, 0, and then lambda. I can get yes from you there, colleagues. All is well? All is
Yes.
well?
Yes, sir.
So now, from this, you are going to come up with your C lambda will be equals to, let's add the, you are going to get negative lambda, you'll have 0, and then minus 2. Then you'll have 1, and then 2 minus lambda, and then 1. You'll have 1, and then 0, and then 3 minus lambda. Can I get yes from you? All it's one?
Yes.
Yes, sir.
Then after this, we go to condition number 2, the procedure number 2. We must find the determinant of this C lambda. We must find the determinant of this C lambda, colleagues. Well, let's expand this along. I know you are very clever. You are very clever. We can expand this along column 2. I'm right, colleagues? Expand along column 2. I targeted the 2 zeros that I see. Expanded along column 2, or you can use any method that you want there to find that. On column 2, you have plus, plus, and then minus, plus, and then minus, and then plus, minus, plus. On row 2, the first column 2, the first one is 0. Then the second one is going to be plus of 2 minus lambda. Then what is the minor of that position? What is the minor of that position? Is minus lambda, minus 2, 1, and then 3 minus lambda. Then the last one is going to be negative 0. Can I get yes from you, colleagues? All is well?
Yes, it's
Are you
correct, sir.
still there? All is
Yes.
well. Then I see 2 minus lambda multiplied by, here I see minus lambda into 3 minus lambda, and then plus 2. I'm waiting for you to confirm if everything is fine, colleagues. I'm doing this for the last time, for the first time. Can I get yes from you that everything is fine? Then what about this? What are you going to have here? What are you going to have inside the bracket? What is
Lambda
going to be?
squared minus 3 lambda plus 2.
Because I'm coming from Vembe side, can I have this maybe first before I do that?
Okay.
Then we have the determinant of C lambda of this. Avenda, where are you? Then I see 2 minus lambda into here is the same as lambda squared minus 3 lambda plus 2. And then if we want, remember there's another condition. The condition says what? Your f of x. Okay, fine. Before I go to that f of x, is it possible to factorize the remaining part, colleagues? I see 2 minus lambda. What about the other two? Is it possible to factorize this?
Yes, sir.
Is lambda minus 2 and lambda minus 1. Eh?
Yes.
Correct,
Yes.
sir.
Do you see that what we have checked on the example here? There is somewhere where you said f of this lambda will be equals to this is 0. Do you still remember that? And
Yes.
that's where you, okay,
Yes.
before you say 0 is the same as the determinant of this is C lambda, which is equals to 0. Can I get yes from you? Then on the procedure number 3 or 4, meaning now you are going to do what? You are going to equate this thing of 2 minus lambda multiplied by, and then this one, if I want, I can write it nicely as minus lambda plus 2, and then lambda minus 2, and also lambda minus 1 equals to 0. Then let's agree. Lambda, the first lambda, the answer is what there? Is it 2, positive 2? And lambda number 2, the answer is positive 2. And lambda number 3, the answer is 1. Can you please confirm if the first one of minus lambda plus 2 is correct?
Yes, sir.
So do you see that the question that we are answering on question number 1, where they gave us that x is the vector x together the matrix, they got that this thing is what? Is what? Is an eigenvector.
Again,
Is an eigen what? Is an eigenvalue, sorry.
yes.
Do you see it? Because if you take this for lambda 1, which is equals to lambda 2, which is equals to 2, what is going to happen? What is going to happen? What is going to happen? You are going to have your C lambda 1, which will be equals to C of lambda 1 multiplied by the variable x. The answer will be equals to this 0 there. Do you agree? So your C of 2 will be equals to C of 2, sorry, will be equals to C of 2 multiplied by this vector. So let's go back. I want you to substitute on this statement. Where there is lambda, put 2. Where is it? Where is it? Where is this example started? I want you to substitute where there's lambda by 2. Please help me on this. Can you please help me, colleagues? What do we have? We have minus lambda, 0 minus 2, 1, and then 2 minus lambda, and then 1, and then 1, 0, and then 3 minus lambda. So now, if you go down to this, what is going to happen? Remember, this one is equals to this, a 0 is going to be equals to a 0 matrix. Then you'll come here and say you are going to have -2, 0, -2. And then you have 1, and then what, colleagues? Is it 0 in the middle and then 1? You'll have 1, 0, and then what, colleagues?
1.
Is it 1 here? Can I get yes
Yes.
from you?
Yes.
Then
Yes,
that
sir.
one of the variable x, let me come up with x1, x2, and then x3. If I want, I can also put this 0, 0, and then 0 there. Can I get yes from you? Are you still
Yes,
there,
sir.
colleagues?
Yes, sir.
Yes.
So for the first one, for the first row, on row 1, what are you going to have? You are going to have negative x1 plus 0x2 minus 2x3 is equals to 0. Do you see it?
Yes.
So from this, what are you going to have? You are going to have minus 2x1 will be equals to positive 2x3. Then your x1 will be equals to x3. Do you see it? Do you see that? Is it minus, ne? Sorry.
Yes, sir.
Minus x3.
Minus.
Do you see it?
Yes.
So if we write everything in terms of, you are going to have your x1, x2, x3. We have already know that your x what is going to be your x3? You are going to have a -1, 0, and then x, and then 1. Do you agree?
Sir,
Yes, sir.
on row 1, isn't it that we are going to have
Whether you use row 1, row 2, row 3, you will get x1 is equals to minus x3. There's no need to carry on. You can check. On x1, you'll get, on row 1, you'll get x1 equals to minus x3. Even if you use row 2, you'll get x1 equals to negative x3. Even if you use row 3, you'll get the very same answer.
okay.
Why one class rep?
Yeah, okay. Well,
Sure. So do you see, this is the x that we got from the previous example. And remember that x came in terms of what? Of -1, 0, and then 1. Do you still remember that? Hello? Do you still remember that, colleagues?
Yes, sir.
yes.
Sure. That's why they are saying the 2 will satisfy that condition of what? Is it an eigenvector? Sure. Then now, let me see if we can come up with something here. Here comes the problem, but I told you that there is something to do with this eigenvalue and subspace. You are lucky for now because you're not going to talk about the theorem or whatever, but let me give you the definition. On the definition, or can I give you this definition? This definition is common, colleagues. You can write it up there. The definition is common. Let A be an n by n matrix, n by n matrix with this scalar lambda, and we are told that that lambda is an eigenvalue. It's an eigenvalue of that matrix A. And then the eigenspace, I guess on Monday, is it Monday? Yeah, Monday, we did talk about an eigenspace. Check the notes for those who attended on Monday class. You were very few. Then lambda is the set where you have this E for eigenvalue lambda will be equals to this vector V such that A multiplied by this vector V will be equals to this lambda of this vector V. It is the subspace. It is the subspace of this n dimension. Are you still there, colleagues?
Yes.
Hello, are you still there?
Yes, sir.
So I don't know, colleagues. I'm not jealous. I don't know if maybe should I give you the statement, but it's not common. The statement of this under this definition, but it's fine.
Sir,
Let me leave. Yes.
Sir,
oh, please.
Yes.
can you please go up?
I guess this definition you are writing it for the second time. Those who attended the Monday class, you still have this definition of eigenspace, if I remember very well. So next year, for those who are going to come back, then you are going to have a theorem that is going to fall after this theorem, after this definition. Please make sure that you pass. Can I get yes from you, colleagues? Everything is fine?
Yes, sir.
Yes.
This one, I don't want to repeat myself, but I don't think you are going to have a problem. Please check this one. This is an example, common example. Find the eigenvalues. You have already done two. The eigenvalues. A, correct. Eigenvalues. After eigenvalues, you must find the eigenvectors. After the eigenvectors, then now you are adding the other term called eigenspaces and eigenspaces. We have now defined what is an eigenspaces there. Eigenspaces of the following. Number one, we have a it's not always that you are going to get a matrix A, colleagues. We can change this matrix A to be another variable, another letter, 2 and then minus 7 and then 4. And then again in number 2, if we have this A which is equals to, you have 1, 3, 3, minus 3 and then minus 5 and then minus 3 and then 3, 3 and then 1. Are you ready, colleagues? Can I do one of this and you'll go and do the other one? Today is Friday.
Yes.
Between A and B, which one can I do? Between 1 and 2, which one can I do, colleagues? Yeah?
2. Number 2.
Number 2.
Let's do number 1, then number 2 you'll do it when you come back the first day after you got your test 2 script, then we can talk about number 2, right? Please go and try it. Colleagues, are you still there?
Yes.
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 Number 2.
Solution for number 1. Solution for number 1. Remember on number 1, we have 2 by 2, which is minus 5, and then 2, minus 7, and then 4. We are going to follow those procedures. I'm right. The first one, you know we must come up with this, which is A minus lambda I. I'm right?
Yes.
Are you still there, colleagues? Then from here, you will say the C lambda will be equals to, can go step by step for now, but from number 2 going up, we are not going to follow all the steps. Minus lambda multiplied by the identity is going to be the size of A. A is 2 by 2, meaning the identity will be 2 by 2. Can I get confirmation that when you add these two, you are going to get minus 5 minus lambda, and then you'll have 2 minus 7, and then 4 minus this lambda. We close here, colleagues. Are you still there?
Yes.
So if you agree, after this, you know that you have a characteristic matrix, then you go to characteristic polynomial. On the characteristic polynomial, that's where you are going to have the determinant of this C of this lambda, which will be equals to the determinant of what? Of A minus lambda I. Can I get yes from you?
Yes.
Then what is the determinant of that 2 by 2? You will get minus 5 minus lambda multiplied by minus 4 minus this lambda, and then plus 14. Can I get yes from you, colleagues?
Say.
Yes, I've done mistake. Is there any wrong?
Yeah, isn't it supposed to be 4 minus lambda? The second
Yeah.
bracket.
Oh, not negative here. Very good. Very good. Yeah, the specs now. Today you got me well, right? Then you have minus 5 minus lambda. It's fine. Multiply by 4 minus lambda. And then the other one of 14 is correct.
Yeah,
Can
it's
I get
correct.
yes from you, colleagues? Then
Yes.
now, when you multiply throughout, you'll get negative 20 plus plus 5 lambda. Please help me. Plus 5 lambda minus 4 lambda. And then what is going to happen? I see positive lambda squared plus 14. Then it's the same as lambda squared. And then what? Plus lambda. And then what is minus 20 plus 14? What is the answer?
Minus 6.
-6.
Minus 6. Remember, the answer for this is the same as determinant of this is C of this lambda. Then we close there. Then on the procedure, you and me, we agreed that there is somewhere where we must have the f of lambda. The f lambda will be equals to the equals to the determinant of C of this lambda, which will be equals to 0. That's when now we are going to have lambda squared plus lambda minus 6 is equals to 0. Is it possible to find the factors of this? Is it possible to find the factors of these, colleagues?
Yes.
Yes.
Is what and what, class rep?
-2.
Lambda plus 3.
Plus 3 and minus
And
2.
lambda minus 2.
Then we get lambda is equals to minus 3. And then also we have lambda which is equals to 2. Is it fine? Is it fine?
Yes.
Yes.
So from now here, according to procedure number 5, let's start for lambda. I don't know, should I write the lambda 1 and lambda 2 there? Or should I write for lambda which is equals to minus 3? So you go back for C of lambda, which will be equals to the C of this lambda multiplied by this variable x will be equals to this 0. Is it fine, colleagues? Then the C of this minus 3 will be equals to the C of this minus 3 multiplied by this variable x, which equals to this 0 vector. So we go back. Can I go back, colleagues? Are you still with me? We are
Yes.
going to start with this one. You are going to replace where there is lambda by. You are going to replace where there is lambda by minus 3 here. Do you see it, colleagues? Where there's
Yes.
lambda, you put plus 3. So meaning your C of lambda will be equals to what? Your C of lambda will be equals to what?
-2.
-2.
Will be equals to minus 2 and what?
2.
And 2 and what?
-7
Minus 7 and what?
and 7.
And 7. Very good. In terms of the x vector, are you still comfortable? You want to work with x1 and x2, or you want to change the variable?
x1, x2.
0 and 0. Are you all there?
Yes.
So from this, what is going to happen? You will see that whether you use row 1 or row 2, colleagues, you are going to get your answer will be equals to x1 will be equals to negative x2. Do you agree? Please check it. Is it correct?
Yes.
Eh? So in terms of colleagues, I'm lying. Why?
Then I got x1 equals to x2.
X2.
X1 equals to x2, right?
Yes.
So if you write this thing in in terms of coordinate x1 and x2, what is going to be your answer? What is x1? You can write everything in terms of x2, maybe. X1 is x2, and then x2 is equals to x2. Do you see it, colleagues? And that's where you are going to have your x2 will be equals to 1 and then 1. Or else you can write this as x bar is equals to maybe x1 and then x2. And that's where you are going to have what? You are going to have x2 and then x2. Then this thing is the same as x2 into 1 and then 1. Are you still there?
Yes.
Yes.
So after this, we go for the eigenvalue number 2. For the okay, fine. Before we go there, we can conclude that this one is the one that is responding to lambda is equals to minus 3. So now we can talk that our sorry, I don't have a space. We can say now our 1 and 1 is the eigenvector, is the eigenvector, is the eigenvector, is the eigenvector, is the eigenvector corresponding. This one is corresponding to what? Is corresponding to eigenvalue. Corresponding to eigenvalue, your eigenvalue that we're busy with is this one when lambda is equals to minus 3. So when you are done with this one, you go for the second one. Or maybe before you go there, you can write that according to the definition. So the basis for the eigenvalue, for the eigenspace, for the eigenspace corresponding to eigen, the eigenvalue of lambda equals to minus 3 is the set, sorry colleagues, I'm trying to get it nice, is the set. Maybe we can say b base, remember is the basis, b minus 3, which is equals to, you have this set of 1 and then 1 for the first one. Are you still there, colleagues?
Yes.
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 So now we are going to check for eigenvalue number 2. Now you are going to check for eigenvalue number 2, which is lambda is equals to 2. Are you still there, colleagues? We are not going to struggle. We simply go back and say C of this lambda will be equals to C of this lambda multiplied by this variable x, which is equals to this 0, this. Then your C of 2 will be equals to this C of this 2 multiplied by this thing. Then we know that it's going to be equals to this 0. We go back to that star again. Do you still remember the equation of a star? You are going to replace where there's lambda by positive 2. Where is that equation? Supposed to be somewhere here. Can you please substitute that star where there is what? You substitute where there is lambda by positive 2. Are you done, colleagues?
Yes.
When you do that, you are going to have
Minus
your
7.
matrix will be what? Minus 7,
2.
2,
Minus 7.
minus 7,
2.
2. The variable, let's use the variable x1 and x2 again, it's not a problem, which will be equals to this 0 and then 0. Are you still there, colleagues?
Yes.
So now, class rep, Ramaklo, Samuel, Ramaklo. Now, either you use row 1 or row 2, you are going to get what? You are going to get, okay, on row 1, I'm going to get minus 7x1 will be added to 2x2 equals to 0. Then what is x1? X1 will be equals to 7 over 2. Hey, I'm lying. 2 over 7 of x2. Do you see it? Do you see it, colleagues?
Yes.
Yes.
So from this, you don't have to worry. We must solve what is x1 and x2. X1 we know is 2 over 7 of this x2. What is x2? What is x2?
X2.
Eh? Eh?
X2.
It's X2.
Serious? All of you colleagues, you understand how we got x2?
No.
You're waiting for me to say that. X2, if you want to solve x2, you'll have 7 over 2 x1 is equals to x2. Am I right?
Yes.
But we are writing everything in terms of x2. If you are writing everything in terms of x2, what is x1? What is x1? What is x1? X1 is 2 over 7 of x2, which will be equals to this x2. Then you'll remain with x2 is equals to x2. Then I'm waiting for you with the red color. Can I write that x2 will be equals to x2 here?
Yes.
Yes, sir.
Did you see how I solved it? You are going to do together with the previous ones, you do them like that. So from this, on the second one, you'll agree with me that you take out x2 as a common factor, you'll have 2 over 7 and then 1, then we close this bracket. Can I get yes from you?
Yes.
Yes, sir.
So in terms of conclusion, you can say what now? We can say our 2 over 7 and then 1 are what? This is the eigenvalue that corresponding to what? That is corresponding to what? Eigenvectors. Eigenvectors corresponding to what, colleagues? Corresponding to what? Corresponding to what, colleagues?
Eigenvalue.
Corresponding to eigenvalue. And the eigenvalue that we are referring to, you are referring to that one of number 2, the eigenvalue which is lambda equals to 2. Do you see it?
Yes.
So now, if we have that eigenvalue that corresponds to 2, then now what is going to happen?
The basis.
The basis of the eigenspace.
Then what is going to be our basis? What is going to be our basis? Okay, fine. If you take 2 over 7 and then 1, you take out a common factor of 7. What is going to happen? You are going to left with what inside the square root? Inside this root?
You'll have 2 and then 1 over 7.
You'll have what?
2 and 1 over 7.
If you take out, okay, 1 over 7, then 2, and then what is going to happen here?
2, yeah.
You'll have
Here
7
it
like
will be
this.
7.
Okay. So, what can you say about 2 over 7? What can you say about 2 and 7? Do you see that this 1 over 2 and 7, you can write what? Maybe lambda multiplied by this variable x, where lambda is equals to 1 over 7, and then where the other part of 2 and 7 will be that variable x. Can I get yes from you?
Yes.
I'm waiting. All right. So now let's check something. From this, you can agree with me if I say we can say now, we can say, is it 2 over 7? What is that 2 over 7? Yes, we can say 2 and 7, right? You can say 2 and 7 is the eigenvector. Do you understand? Since you said lambda multiplied by vector v, vector what? Vector x, man. Then now you are saying is an eigenvector corresponding. It's an eigenvector corresponding to lambda equals to this 2. Do you see it?
Yes.
So if you want to check, it's not a problem. Remember, there's somewhere where you said a of this will be equals to this lambda of this. I'm right? You can take your left hand side and your a is what? What is your a? Your a is minus 5 and then 2.
2 negative
Minus 7 and
7.
then 4. Is it the correct a that we have, or is when you substitute where there's lambda by 2? Remember, when you substitute lambda by 2 on that star equation, you got this. Or this one, is it the original a? Okay, fine, let me check. Yes, is the original
The
a,
original
colleagues.
one.
Is the original a. I'm right? Multiply by this part. The red part, it's where now you have this 2 and a 7. When you multiply this, what is going to happen, colleagues? You are going to have minus 10 plus 14, and then a minus 14 plus 28. Is it correct?
No.
I'm waiting, colleagues. You can use your calculator.
Minus 14.
Is it minus 14?
Yeah, plus 28.
Wait. You said the red part minus 10 plus 14. Is it correct?
Yes.
What is the answer there?
Oh.
Even now. Minus 10 plus 14, you don't know. You want to use a calculator.
It's 4.
It's 4.
It's 4.
Even Trust you don't know this. Minus 14 plus 28 was the answer.
14.
Yeah? Is it
14. Yes.
So if it's 14, you can take out the common factor on this. When you take out the common factor, what is it? Is 2 into 2 and 7. Do you see it?
Yes.
And I can say this multiplied by this. Colleagues, please enjoy your holidays. I will see you when you come back. Please make sure that you come on time. On Monday, the 29th, you are going to get your script. Hopefully, we'll arrange with you through Blackboard. We did not finish this question. We must talk about the eigenspace. We'll address that one when you come back. But in the meantime, please try it on your side. Is it fine?
Yes.
All right.
Yes.
Take care, colleagues. See you again.